All right, hi everybody. We're talking about the second law of thermodynamics today, chapter 3 of Atkins. Specifically, we're going to talk about the Carnot cycle. And this is essentially a history lesson, but I hope that it helps whet your appetite and sort of set the stage for what we're going to be talking about throughout this chapter. And in the sense of history, I had to show you this the last time that I had taught this. I had this slide there at the start. October 2017, Tom Petty died. It was a sad day. A little light of humanity went out. But if you're looking for any music recommendations, you can check out these albums. They're among my very favorite. Okay. So to set the stage, the first law of thermodynamics tells us what's possible, right? The types of changes that are possible. Specifically, we have to have changes that conserve energy. But it doesn't tell us what actually happens. And there are lots of examples of this. So imagine this situation where I had a stopcock, which is filled on one half with gas and vacuum on the other half. And I imagine doing this all isothermally. I pull the stopcock and what happens? Well, the gas spreads out, right? Not rocket science. And we know that this happens every single time. There is nothing in the first law of thermodynamics that would preclude the same set of gas molecules from all showing up over here, right? Yet it never happens. Gases will always spread out and they will never spontaneously structure themselves like this. Okay, here's another example. We're in upstate New York. Winter is coming, and if we sit here long enough and we have a car like this, what will happen over time? Well, it will rust, right? Iron in your car will spontaneously oxidize and form iron oxide. We know what is better known as rust. Yet there is nothing, I gotta move this thing up here. I'm gonna go like this. All right, there you go. There is nothing which would preclude rust from spontaneously forming iron and oxygen, yet it never happens, right? So why doesn't the reverse reaction happen? Well, the answer to all of these questions is in general the second law of thermodynamics. I'm going to scooch this out of the way a little bit. This is one of the real joys in studying thermo, learning about the second law of thermodynamics. And you'll find lots of popular references to it. You can check these out, but I'll read them to you because they're worth sharing. The second law of thermodynamics is, without a doubt, one of the most perfect laws in physics. Any reproducible violation of it, however small, would bring the discoverer great riches as well as a trip to Stockholm. The world's energy problems would be solved at one stroke. It is not possible to find any other law for which a proposed violation would bring more skepticism than this one. Very true. Second, nothing in life is certain except death, taxes, and the second law of thermodynamics. All three are processes in which a useful or accessible form of some quantity, such as energy or money, are transformed into useless, inaccessible forms of the same quantity. That is not to say that these three processes do not have fringe benefits. Taxes pay for roads and schools. The second law of thermodynamics drives cars, computers, and metabolism. And death, at the very least, opens up tenured faculty positions. Last but not least, if you're a Woody Allen fan, he says this: it's the second law of thermodynamics. Sooner or later, everything turns to shit. Okay. So with that ominous introduction, let's get into the Carnot cycle. Specifically, what I want to talk about here are engines. We're talking about engines from a chemist perspective. So it's going to be very, 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 very qualitative. Here's an engine, right? And here's what an engine does. It takes heat, right? Input heat, or what we will call a heat source, and it converts it into work. I'm not concerned with the internal workings of this engine, how it actually does it. I just need to recognize that it takes heat and transforms it into work. There's one important caveat though. And that is that engines always have waste heat. Right? If you talk to your engineering friends, we call the input a heat source. Engines always have to have a heat sink. Right? So there's always some waste heat that's produced. The second thing to know about engines is that they have to be cyclic. Right? So imagine a piston. There's some little spark plug in here, right? It might expand and sort of drive the cam and internal combustion engine, right? But then it has to compress back, and engines always have to be cyclic. If they only run once, it doesn't do us any good. And way back when, in 1824, right, this is the guy who was thinking about this. His name is Sadi Carnot. He was a French military officer. And what he was thinking about is, how do I maximize the efficiency of an engine? I always like this picture because you can get some sense of about how old he was. Right? You can see his youthfulness in this picture. Here's what Sadi came up with. He envisioned a 4-step cycle that could work in some hypothetical engine. This isn't an actual engine cycle, it's a hypothetical process, but it has 4 steps and it reveals some important things. Here are the 4 steps. We start up here at some high temperature, a hot temperature, and we undergo a reversible isothermal expansion. At some point we stop, and we go to step 2, which is an adiabatic expansion to some cold temperature, call it TC. We then start running in reverse, and we do an isothermal reversible compression. Last but not least, we do an adiabatic compression back to T hot. Okay, so these are the 4 steps: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. And what you might imagine doing, as you've done in some of these other practice problems, is going through and starting to fill out a chart that looks like this. You calculate the heat that you have to input, the work, the change in energy for all of these steps. I'm not going to go all the way through it, but here are the answers. So, for instance, in step 1, it's an isothermal process. So delta U is, if I can get my marker up there, my cursor is 0. Here's our expression for work, negative nRT, natural log VV over VA. You calculate Q. Step 2 is an adiabatic expansion. So the heat input is 0. Here's our expression for work, and then change in U. You can go through and do all this, and if you're bored, you can verify all this. What Sadi thought to do at this point was, if I'm thinking about how to maximize the efficiency of an engine, I had to define efficiency. And the way he defined it is as follows. The efficiency of the engine is the work output. The lines here are indicating an absolute value. Remember that work output would be a negative. So you put absolute value of work over the heat input, QH. And I'm going to work through some things. So let me switch my cursor. Pointer, pen. I don't like to write in red. I'm going to write in black. And calculate what epsilon is. Okay. So the first thing I need to do is calculate work total. And I'm going to add up all of these columns. Well, what you might be able to see right away is that the work in steps 2 and in steps 4 will cancel one another. Here I go, temperature hot to temperature cold. This is the reverse. So those two will cancel each other. And what you end up with is an expression then that looks like this. nRT hot, natural log, B, A minus nRT cold, natural log, B, D over B, C. I don't know why my pen always jumps like that, but it happens. All right, this is my expression for the total work. If I add up all of the entries in this column. And now I'm going to calculate efficiency. Because I'm taking the absolute value, these two negative signs are going to go away. And I'm left with this, nRT hot, natural log VB over nRTC, natural log VD over VC. And I'm going to divide all of this by Q hot. Remember, the heat input comes in step 1. This is where it's absorbing heat. nRT hot, natural log VB, VA. Simplify, what you can see is that this term will cancel with this term. And in addition, I have this NR, which is going to cancel with this NR. So what I'm left with is something which looks like this, equals 1 plus TC over T hot, natural log VD over VC divided by natural log VB over VA. Okay, at this point, we need to make a little simplification. And this isn't necessarily obvious. It's not hard to show using our expressions for temperature and volumes in adiabatic expansion. But it will turn out that the ratio of VB to VA is equivalent to the ratio of VC to VD. Right? Or in other words, this expression is true. And if I take that and I plug that into what I just had, efficiency equals 1 plus TC over TH, natural log, this was VD over VC, plus, I'm now going to make this substitution, natural log VD over VC. I have this to the minus 1. Remember that if I have natural logs, I can take these exponents and bring it down there. And then this term will cancel this, and you're left with this important result. Epsilon is 1 minus TC over TH. In other words, to maximize the efficiency of the engine, you want the largest temperature difference that you can get. Okay. It will turn out that Soddy, in fact, here discovered the second law of thermodynamics. One of the annoying things about the second law of thermodynamics is that there's at least 3, probably 4 or 5 different ways that people say it. But this is one of the statements of the second law of thermodynamics. So it is impossible to devise a heat engine, the sole result of which is the conversion of heat to work with 100% efficiency. This number can never be 1. It is always less than 1. And I always have to have a heat sink. Here was Soddy's particular genius. He didn't stop here, but he asked this question of why. And let me show you what he recognized. Here's this table of thermodynamic variables for the Carnot cycle. I always have to have the heat sink, right? That is this step here. This is where the Carnot cycle spits out heat. And what Soddy recognized is that these terms look really similar. So let's say I instead here thought about Q divided by T. if I did that, what you would get in this expression is NR natural log VB over VA. Here you get 0. Here the temperature is going to go away, and you get NR natural log VD over VC. And here you get 0. Okay, big deal. The last thing Sadi did was he used this expression here to substitute in for this. And so I'm going to write in red now. This equals negative NR natural log VB over VA. Sum these things up, right? This is a cyclic process. So if I were to look at the total change in, my head's probably in the way. If you were to look at the total change in internal energy, delta U, right? I know that this is a cyclic process, so the total change has to be 0. And it is. You can calculate the work that's in here. It's the area bounded by this, but you'll find that it's not 0. You have to put heat into it. So it is also not 0. Right? But look at this quantity here. If you sum all of this up, this term will cancel this. Right? The total sum of Q divided by T is also 0. What this means in words is that there is some quantity, whatever this represents, Q divided by T, which is conserved in a cyclic process. I start at one point, I get back to the same. In other words, it looks like a state function, like internal energy. Okay, I'm going to stop here, and I'll tell you a little bit more about how we define entropy next time and connect it here with this definition of Q divided by T. See ya.